Hello everyone. This video will be on the 3.6 section of the IB/AA curriculum. Please pause the video for a second to look at the concepts, contents, and formulae for this section. One sentence that summarizes this section is, use trigonometric identities to move freely between sines and cosines. In this section, you can find some interesting equations on the formula booklet. What are they? Well, they're not technically formulae, they're called identities. Identity is defined as the equality of two expressions for all values of the quantities expressed by letters. Why do we want to know these identities though? We can use a trig identity to transition between the trig functions. If you have sine x, you can go to cos x, and vice versa. Also, you can express a difficult expression into a simple and neat expression. Doing this will help us solve some equations, especially in the 3.8 section. We will see how they happen. So, let's look at the identities. The first one is called the Pythagorean identity. And as the name implies, the shape of the Pythagorean identity has that of the Pythagorean theorem, right? Where would you use it? Well, since the Pythagorean identity has a square on the sines and cosines, whenever you see these exponents on trigs, you can assume that you're using the Pythagorean identity. Let's look at the example below. The goal is to simplify the expression. Well, the first thing is that there is a common factor in both terms, so let's take that out. Then, we know from Pythagorean identity that the expression in the bracket can be expressed as 1. Okay, so over here, I'm going to say Pythagorean identity. Say cos theta of 1. Now, we just get cos theta. When you're using the identity, it's a nice idea to write down the name of the identity. Okay? See how simple it looks now, right? The next identities are called double angle identities. As the name implies, double angle identities are useful when you want to find the sine or cosine of twice the given angle. There are two identities, the sine of 2 theta and the cosine of 2 theta, depending on what you need. And also, the cosine of 2 theta has 3 versions. You can pick and choose what you want to go with, also depending on what you want or what you have right now. Let's try this question over here. Looking at the shape, at first you might think it's a sine squared, 2 sine squared of 3d, so could we use a Pythagorean identity here? Okay, well I know that since sine squared theta plus cosine squared theta equals 1, then sine squared theta is equal to 1 minus cos squared theta. All right, let's try that. 2, 1 minus cos squared 3d minus 1, and therefore we get 1 minus cos squared 3d. Well, we didn't get anywhere, so I don't think that's the right idea, right? So let's scratch that. Now let's go back to the double angle identities on the formula booklet and see if you can find any expressions that look similar to 2 sine squared 3d minus 1. Right, so if you look at the double angle identity for cosine, the cosine 2 theta is 1 minus 2 sine squared theta. Okay, so I think we can alter the form right now to match that style. I think I can do that by dividing by -1. This will be 1 minus 2 sine squared 3d. And knowing that this expression inside the bracket can be expressed as cosine 2 theta using the double angle identity. This will be -1 of cosine 2 and then 3d. And I think we can express that as negative cos 60. See how that's kind of magical that we went from this 2 sine squared 3d minus 1 into just one simple negative cos 60. Let's look at the last example. This was taken from the guide. Given cosine x is 3 over 4 and x is acute, find sine of 2x without finding the x. Okay, well, first thing is that, okay, if I want to find the sine of 2x, let's look at this double angle identity. Sine 2 theta is 2 sine theta cos theta. So let's write that down here. Sine 2x equals 2 sine x cos x. And I know cos x is 3 over 4, so that would be 3 over 2 sine x. So we know that to solve this problem, we want to figure out the sine x first. Okay, but how can you find the sine x using the information given to us? Well, I think we can use the Pythagorean identity. So let's take out the Pythagorean identity. Sine theta squared plus cos theta squared equals 1. And I know that using the cos x, if I isolate the sine x here, sine squared theta equals 1 minus cos theta, and then sine theta will be square root of 1 minus cos squared theta. Let's just do that because we know cos x is 3 over 4, so cos squared should be 9 over 16. This is 7 over 16. We can say that this is square root of 7 over 4. Using the value, we didn't solve for x at all. I know that should be x here. Actually, let's try like that. And we can say that 3 over 2 times square root of 7 over 4. We know that at the end, this is 7 over 8. So, these identities become extremely helpful in the rest of our journey in trigonometry. Always have in mind that if you don't like what you see in front of you, you can change it up using these identities and get something simpler. Think of them as a wild card in Uno, where you can change the color of the card if you don't like it. I hope you enjoyed this video, and try some questions in this section to really master the skills that we have learned. Anyways, I'll see you in the next video. Best wishes.